So then I'm very delighted to introduce Pierre Gentine, who is a professor of geophysics at Columbia University. Pierre, do you want to share your screen?
Yeah, thanks a lot for the invitation. Is it full screen?
Yes, it is.
Okay. Let me know when you want me to get started. I don't know if you want to stick with the time or.
Well, yeah, maybe we stick with the time. We just give it one more minute. And in that minute, maybe you can talk about machine learning and how, your relationship to machine learning, how that came about.
Sounds great. Yeah. Just give me the green light. Thanks.
No, I mean, you could just, while we're waiting 1 minute, you could talk about that right now.
Yeah, so I came along because I basically started developing some new parameterization for convection, and I got really frustrated because I was really happy at first, and then I started to get into the weeds, and I said, I will never get there, at least not within a time frame reasonable for climate change, So, and that's when I started to think, okay, maybe because I was using machine learning on the side for some other things, for like satellite data, I thought, maybe that's the best tool we have right now to actually tackle that within a reasonable time frame, And I just thought that it was just too pressing, There was just too much pressure, timeline was too short, and the development of parameterization was just too slow, So that's where it came from.
That is a great introduction. And with that, I would say, let's start your talk. Thank you.
Thanks. Yeah. So today I wanted to talk about, and thanks a lot for the invitation first. I wanted to talk about something I've been really interested in over the last couple of years, is to try to bridge between physics and machine learning. And Tim gave a great introduction as to why we would want to do that, especially the fact that we have conservation laws, but not only. So I will try to explain why we got really interested in that. A lot of that is actually work from Tom Buckler. He was a former research scientist in Mike Pritchard's group and my group. He's now at University of Lausanne. He has a lot of offers right now, so please look him up. And Stefan Rasp also in Germany, in a startup right now. So really, what I wanted to discuss today is really looking at the hydrological cycle and looking at clouds and convection in particular. And Tim gave a great introduction to talk about those things. And the reason why I got interested is when we start thinking about climate change, a lot of the projection that we get from climate models is really, really uncertain. And a lot of those uncertainties is basically related to small things like clouds, And what it means is that those small clouds that we cannot directly resolve because the models are really coarse, actually strongly regulate actually the global temperature change for a given amount of greenhouse gas concentration. And that's some nice work by Tapio Schneider and Florent Briand, looking at what will be the response of basically what we call climate sensitivity. So that's basically the equilibrium temperature of the planet for a given amount of CO2 concentration in the air. And you can see that every circle here is basically one climate model. And you can see that there's actually a vast variety of different answers in terms of what will be if you will, on the x-axis is like the inverse of temperature for a given amount of CO2 concentration. So there's this really wide range, and you have some models that are very aggressive. It means that you will need to have very low CO2 concentration to reach a higher temperature, and some models that are a little bit more optimistic, saying, okay, you can actually go a little bit further in terms of CO2 concentration, you can emit a lot more, and then the planet will be actually a bit cooler. And actually a lot of that can be directly related to clouds. And in fact, here that's related to low cloud reflectance. And in fact, it does make sense. I mean, the more clouds you have and the brighter they are, the more reflection you will have back to space, and therefore the cooler the planet will be. So you will have this kind of damping effect, feedback, as we call it, as opposed to some amplifying feedback if the clouds were to be fewer or if they were to be darker, basically. So they are absorbing more. Okay. So what it means is that feedback is actually crucial to understand and project the change of the global temperature, but not only temperature, also the water cycle and all sorts of things like droughts and heat waves and all sorts of things that are responding to climate change. And that's basically a lot of what is actually controlling what is here in the red box, which is the Paris Agreement. I mean, the IPCC just got released today, the report. And so we typically use 2 degrees as global temperature warming compared to pre-industrial. And you can see that's basically related directly to the amount of CO2 concentration you will have. And that's vastly varying across climate models. And that's really a major roadblock for policy making and a lot of the impact we want to have as a community. It's not just a global issue that we have here, it's also very much at the regional scale. That's some really nice work also by Sandrine Boni and Bjorn Stevens, looking at what would be the impact of regional radiative effect and precipitation for 4 degrees of warming. So in that case, what they did is they took what we call an aquaplanet, so just ocean everywhere. You bump the temperature of the ocean by 4 degrees, and you just want to see what will be the response of the climate. And every column that you have here is basically a different model. And you can see that it vastly differs across different models. So some models are going to see an increase in precipitation in the tropics here, a drying in the subtropics, and you could see the converse, almost the opposite, if you take another model. And the issue is that what we typically do is we take the multi-model mean, and that will be the best prediction or the best projection you will have. But of course, maybe only one of them could be right, and the other ones could be completely off. And again, that's a major issue, because what you would want to predict or project is going to be the regional hydrological cycle change, right? You want to say, will we see more droughts? We will see an intensification in extremes and precipitation. So those are things that are crucial for people to basically to adapt to climate change. So we need to give a much more accurate type of response. And as you can see here, in that case, we are purely forcing the atmosphere. So it means that a lot of that variability that you saw here in the first slide and the second one is actually just due to like some very small scale processes in the atmosphere. And that's what we typically represent using a so-called parametrization. So that's what Tim introduced before. And that's basically a subgrid representation of things that are basically too small to be represented at the scale that we have in a climate model. And a typical scale would be roughly 100 kilometers or so. And so a lot of those clouds or convection, so deep clouds that are typically precipitating, we need to be represented in a statistical sense, right? And they will need to look at what will be the mean effect of those onto the grid. And you can frame that in terms of a closure, as Tim said, but if you look at the rate of change, we typically write that as a tendency. What is the change in some particular variable? It could be temperature, moisture, or something, or some scalar, or momentum. And what is the rate of change that's due to clouds, or convection, or something else, or turbulence, okay? And that should be just a function of things that you're resolving at the core scale. So just the grid average, okay? The grid average temperature, the grid average moisture, et cetera, okay? And what we do is we do that typically using a physically based approach. So we have some mechanistic understanding of clouds, of convection, of turbulence, and we are trying to represent that directly onto that grid, right? But the issue is that a lot of the spread you saw earlier is actually just coming from the diversity and the zoo of basically parameterizations we have, and even sometimes some fine tuning of some of the parameters for the exact same parameterization can actually lead to vastly different responses, okay? And that's led to what we call some sort of roadblock or deadlock in the so-called parameterization, as Dave Randall actually showed back in 2003. Okay, and that largely explains the intermodal spread in climate projection. And that's a major issue that we need to solve as a community. So what we thought like a couple of years back is that maybe a way to tackle that would be to use cloud resolving models, so simulations that are roughly of the order of a kilometer or so. And we know that those simulations can actually resolve clouds or deep clouds or convection relatively well, okay? And they resolve many of the biases we have, such as the diurnal cycle. They can have some sort of mesoscale convection. They have convection at the right place. And so maybe what we could think of is basically using those and learning from those simulations, even though they might be just over a short period of time, and using them as kind of a template for how we should actually deal and represent convection in a cost resolution model. Okay, and that's one example of such a cloud resolving simulation. So that's basically what we decided to do. And so we took some cloud resolving simulation. If you want it to be precise, it's actually just a 2D. We can get into the details. No need to get into that here. But basically, you have a cloud resolving simulation, so fine scale resolution simulation. You coarse grain that to the scale of the climate model, so roughly 100 by 100 kilometers. And then what you do is that at that coarse scale, you actually learn basically the salient features of convection, right? You want to say, what's the tendency of temperature or moisture? as a function of things that I'm resolving at the scale of the large scale grid, right? So basically you will have as an output the rate of change of temperature due to convection, so deep clouds again. Moisture, so Q is specific humidity, as a function of temperature, moisture, so specific humidity here, and you also have like surface boundary conditions, okay? And you could use many different approaches. Again, you could use a physically based approach. In our case, we said, let's learn from those cloud resolving simulations, and let's build that link and that statistical relationship using a neural network. Then we use some other ones. But basically, you can learn that relationship, and you can fit those neural networks on those simulations. Okay, so it's basically a data-driven approach as opposed to a physically based approach. And when we compare that to the actual fine-scale simulation here, again, constraint, which is at the top here, you can see that we are doing a pretty good job. So here is precipitation at the surface, outgoing long wave radiation, just to up to 2D snapshots. And you can see that basically there's a very good correspondence between the two different simulations, the middle one here being the neural network representation of that. We call it cloud brain, okay, or C-brain now. And you can see at the bottom the difference between the two. So you can see that there's pretty good agreement in terms of where is the location of precipitation and where is the intense precipitation going on. Okay, it's not perfect. You can see there are some spikes. And in fact, if you were to look into that, you can see it's actually very much stochastic. And you can see that the field we are actually getting from the neural network is too deterministic in a sense. It's too perfect, right? So we would want to add a little bit more noise. Okay, but that's something that needs to get into. The advantage is that we are way cheaper than the high resolution model, so roughly 10,000 times, 1,000 times. But we're also even cheaper than the cost resolution model because it's basically a bunch of matrix operations. So it makes it even cheaper than the original parametrized convection system. Those were based on individual snapshots because we, as Tim said rightly, I mean, then simulations will diverge if we were to initialize them differently. So at every time step, we're actually comparing what will be the impact of the neural net as opposed to the actual high resolution simulation. But we also coupled directly the neural network. So we took off the regular parameterization and plugged the neural network and said, okay, what will be in that case the impact? We cannot track individual trajectories, again, because the flow is chaotic, as Tim said. But what we can do is we can compare statistics, right? So we can look, for instance, at extremes of precipitation or distribution of precipitation. And what we found in that case is that the neural network, which is here in red, was compared really favorably to the high resolution simulations, which is here in blue, okay? And also doing a much better job than the original physically based parameterization, which has the typical, what we call drizzle problem, where precipitation happens too frequently and also tends to be too weak. So we don't have enough extremes of precipitation, and that's a major issue when you want to look at the water cycle in particular. Yeah, so we thought that was good news. We're actually excited. We also looked at wave propagations. We were really excited, and then the issues started. Okay, so the first one was the first issue we found was really one of physical constraint, right? So we started looking at the energy balance of within like different columns, and you can do it across the globe. And here are different, basically samples from those different grid cells. And you can see that those are different budgets. So the simulated energy balance as opposed to the actual one. And you can see that we are pretty much on a one-to-one line. So it's pretty good, right? It means that the neural net has kind of learned that there was an energy conservation. But it's not perfect, right? And in fact, you can get deviations of sometimes like hundreds of watts per square meter. And that's a major issue because climate change is a few watts per square meter. So you would want to be like perfect, right? I mean, you want to be spot on and you cannot lose energy. So it means that even though we are doing a decent job in terms of like spatial and temporal representation, we don't have energy conservation and we don't have mass conservation, and they only approximate with the algorithm. The second issue we found that's a major roadblock as well is one of generalization. And what we did is what we basically did the same experiment I showed you before. You take the ocean and you bump the sea surface temperature by 1 degree Kelvin, 2 degree, 3, and 4 degree. Okay, and you can see basically the expansion here of the circulation and the contraction here at the equator. And we said, okay, can the coarse resolution neural network actually replicate that in the online simulation? And what we found is it just failed miserably. In fact, it failed the very same way that many parameterization do, using and having basically a double ATCC, you know, the typical issue that many physical parameterization have. Okay, so we're really disappointed when we saw that. We say, okay, basically that's a major roadblock, because it means that what we learned in the historical climate cannot be used in the future, and basically defies the purpose, right? So that was basically a major roadblock, we thought at the time. And then we just wanted to know, is it a purely extrapolation issue, or would it be something else? Is it more of an interpolation issue? And so what we did is we trained on like historical climate, so 0 Kelvin, and plus 4K, so basically the future, but really warmer. And we said, if we know those two climates, can we interpolate things in between, right? And that's basically what you will have at the bottom, and it does a pretty good job, right? So it's really showing that it's really an extrapolation issue and not just an interpolation one, right? So you need to kind of extrapolate better, and you at the same time need to conserve physical laws, right? So some summary of the issues: basic machine learning algorithms on your nets in particular do not respect physical laws such as conservation of energy and mass, but those are strict requirements for climate change. And there's also issue with out of sample generalization, right? So as long as you stay within the range of prediction, you're in good hands, and those algorithms work really well. In fact, they are hard to beat, as Tim said. But as soon as you're like out of sample, and climate change is all about out of sample prediction, the issues start, right? And extreme events are another type of similar issue, where a lot of that you've never seen before, especially of the scale. I mean, we're seeing that on a day-to-day basis now. So you could think of that, maybe one way to tackle that would be, what if we were to actually influx a little bit of the knowledge we have, right? We are not in the dark, right? I mean, we have years and years or decades and centuries of knowledge, of physical knowledge, and maybe we could influx some of that, right? So the typical machine learning algorithms are really sitting here, right, on the left-hand side, where you have so much data, but also you're really staying within the same distribution that you can just deal with the data, and that will do an amazing job, right? And we are seeing that on a day-to-day basis, you know, with many of the machine learning algorithms we have. But what I'll discuss in the rest of the talk is when we actually are missing some data, either on the extremes or there's a shift in the distribution. So how can we actually deal with that by using some of the physical knowledge that we have? And that's what we will refer to as a hybrid type of modeling. Okay. And sometimes you can be really data poor, so you're also like undersampling, so you also have some sampling or selection bias. So I won't discuss that today, but so let's focus mostly on like when we are actually missing or there's a shift in the distribution. So the first thing we can do is actually trying to constrain some of the physics, right? So we have some physical laws like energy and mass conservation. But what we could do is we could actually directly bake them into an algorithm, right? So you could take your network, which is here in blue, and you could say, let me add some layers, right? So you would have some hidden layers. And those hidden layers will actually be every time, every layer will be, additional layer will be a conservation law. Like you will have one for some mass conservation, one from some momentum conservation, and you keep adding them. And instead of training on your network and then trying to tune that, you could actually train the whole thing end to end, right? So you could say, I'm training my neural network, but also imposing some layers that are combining different inputs that I'm using from the different previous layers. And I'm combining them in a way so that I can train the whole algorithm end to end. What it means is that you train your neural network, so the data-driven part, but at the same time, you're always conserving energy and mass or whatever conservation laws you have at the same time, because it's again baked within the neural network. And it works really well within numerical precision. So if you're interested, Tom just published a paper on that in PRL. And really it works well, and you can have nonlinear functions and things like that. So that tends to work pretty well. The second issue we wanted to tackle is one of generalization. So we say, okay, let's go to a very extreme case, right? Let's go to a +8 Kelvin experiment. And what we would want to do here is we would want to say, can a neural network train on historical data be able to actually predict or project the future? So the truth here would be that's going to be the moistening here in the some latitudinal average. And that's going to be the heating rate, again, over some latitudinal band, doesn't really matter what it is. Okay, so moistening and heating, those are the targets we want to have in the warm climates. Okay, so those are the anomalies. So if you just use a neural network trained on historical data, you will get that. Okay, so you will get something that's completely off, and that's what we saw earlier in the talk. Basically, you're failing miserably. Okay, it doesn't work at all. Your moistening is like just orders of magnitude and sometimes even in the wrong direction. So it just doesn't work. Okay, so something is fundamentally flawed in the way, so in fitting on your network on historical data. But what if you start using a little bit of your physical knowledge or some of your physical understanding? So what we know is that humidity is not going to be conserved, right? We know that the holding capacity of the air is going to actually increase with climate change. But what we do know is that relative humidity is bounded, right? It's between 0 and 100%. And what's going to bound that is the saturation water vapor, right? So if we are now starting to use relative humidity as opposed to specific humidity, even though those are correlated, you could say, in fact, it's doing directly a very much better job. So that's going to be the result you're going to get here in terms of the moistening and heating, right? So right away, by just adding a little bit of physical intuition, you're actually getting much better result and much better generalization. You can actually get to some additional physical knowledge. You can add, that's not the right wording now, but you can add buoyancy. We know that buoyancy is actually very important for the parcels in the air and for the updrafts. And you could do some rescaling as well. So instead of using temperature, which we know is actually shifting with climate change, you could use buoyancy, which is just an anomaly compared to the surrounding and the environment. Okay. And when we do this temperature or buoyancy rescaling, we're actually getting even closer to the truth, right? To the projection in the future. And that's in terms of the input, but you could also do the same for the output as well, right? You could say the fluxes, the output are also going to change, but we could also rescale that based on, say, the surface fluxes that we are actually projecting as well. And that's going to get you even closer to the end result, right? So what it means is that by adding some physical constraints or physical intuition, you're getting closer and closer to something that's basically climate invariant, right? So something that will actually work, even though it's only trained on historical data. And that's very useful if you wanted to use, for instance, satellite data or something that cannot be generated in the future or where you don't know the processes in the future. Okay, so a quick summary of that would be, you have your original PDF, say, in terms of humidity. You would want to rescale that in terms of things that are relatively distribution invariant. And if you were to directly use the brute force mapping here, what you will find is that the PDF are fundamentally shifting in terms of the output. But if you use the climate invariant mapping, in that case, the PDF, the rescale PDF will actually be almost unshifted. So that's the intent, right? You're not doing any sort of out of sample prediction, and that's the ultimate goal, right? So going to influx and physical knowledge, so you avoid that shift in the distribution. Okay, so quick conclusion. So machine learning is really appealing, as Tim mentioned, for climate processes and in particular for representing physical processes. And I hope I showed you some example where it works for deep clouds, but again, there were some issues related to conservation and generalization, right? And physical invariance. So those are things we want to tackle. And I hope I convinced you that if you were to actually bake in some physics directly into the structure or the architecture of the neural network, or by having some physical knowledge based into that, then you can actually tackle many of those issues, we hope. Okay, with that, I'll finish. And if you're interested, we also have one example for evapotranspiration with the same type of approach. Thank you.
Thank you so much, Pierre. So we have one question here, Silo, that is there a diagnostic that will tell you when the machine learning is in extrapolation mode rather than interpolation mode? It is not obvious since it is multivariate.
Yeah, that's actually a great question. Yeah, so actually the way we do it is mostly with the marginal, so mostly univariate, but that's true. Yeah, it's not straightforward to directly do it in the multivariate, especially when you start going to higher and higher dimension. Yeah, that's a very good point. If we had a way to do that and test that, and you also need to have the right data to test that. So in our case, we're in good hands because we can actually generate some like artificial data, but if you don't know that a priori, that can be tricky. I mean, you could use a colder climate that from the past, you know, as a way to test that. But those are, yes, very good questions. Yeah, I don't have like a recipe, let's say. Yeah, we are doing that as we speak. And Tom will have the paper out so soon, so it will be on archive. So if people are interested.
And that's Tom Buchler. Okay, now questions keep popping in. Next question is, what is the meaning of brute force mapping and climate invariant mapping? Are they implemented by physical models or data-driven model?
So by brute force, what I meant is a pure machine learning algorithm just trained using some data. So basically, you give the problem to a computer scientist that wouldn't have the physical knowledge, right? So they would just say, okay, give me that input data, or input features, those input features, and I'm gonna give you the output. And it seems to work well on some specific data set, which is basically the current climate. But it does fail when you start looking at future climate, right? For the reasons I mentioned, because in fact, there will be a shift in that distribution. For instance, temperature is going to be warmer. The humidity is going to be way more humid or higher. So implicitly, there's going to be a shift. A climate invariant is basically using some physical knowledge where we know that relative humidity is basically not changing dramatically across the globe, where buoyancy is going to be in terms of the anomaly. So those are things that are not dramatically shifting. So we know that we are actually baking some constraint in terms of the range that we have, you know.
So we have 3 more questions, but I think we probably only have time for one. So I will pick the first one. Can you clarify how you include RH? I guess that's relative humidity. Did you add a constraint layer for RH or just as an input variable?
Just as input variable. So there's just an additional variable where you have temperature, humidity, you go into relative humidity, pass it on to a neural network, and then you can go back to your, because at the end, what you want is you want to have the tendencies in terms, again, of the same thing as before in terms of, in terms of temperature, right, which was the original variable. So you need to go back to the original variable. So there's just a little bit additional work to get to those climate invariant variables, and then you go back to the original ones that you wanted to predict, because they are the ones that are in your climate model in particular, like temperature or specific humidity, or it could vary depending on the climate model.
Great, thank you.